Hi everybody, and welcome back to Chemistry at Woodbury Forest. Today we're going to talk about reaction mechanisms. So let me show you something interesting here. So we've seen that reaction a bunch of times before. That is the combustion of propane. We're taking C3H8, combining it with O2 to make CO2 and H2O. So now, one thing that we haven't paid attention to before in talking about how reactions happen through collisions between particles, well, really we just have to kind of look at this really closely and you may be able to see it. Okay, so come up close. Oh, wow. Okay, so that is so cool. Can you see that? You got to look right in closely and pay attention. You're looking, try and see if you can see some of the molecules there. So we've talked about propane and oxygen combining and making CO2 and H2O. Oh, but right there, did you catch that one? Okay, so there was a molecule that wasn't a CO2 or an H2O. It was some kind of combination of carbon with a couple of hydrogens and maybe an oxygen stuck to it. Oh, there's another one. And but those things aren't there at the end. Can y'all see? Okay, so I'm messing with you, obviously. You can back off now, don't burn yourself. When we do that, when we make C3H8, propane, and oxygen combine to make CO2 and H2O, even though I can't see the molecules, I can guarantee you that that process isn't happening through just a single collision of those molecules to break apart into products, sort of like the processes that we've talked about up to now. How do I know for sure that that's not happening that way, even if I can't see the molecules? Well, let's consider the reaction for a second. Propane reacts with oxygen to make CO2 and H2O. Here's the balanced equation for that. So let's think for a minute what that would need to look like for that to happen in a single step, just one collision, making all of that stuff go. All right, so we've got a propane molecule. We've got 1, 2, 3, 4, 5 oxygen molecules. And so let's see if we can imagine 5 molecules colliding with propane and breaking apart as 3 CO2s and 4 H2Os. That's pretty tough to conceptualize, right? If we think about what would be required in order for this to go, even the very first requirement that 6 molecules, 5 oxygens and a propane, come together in the same place at the same time is itself difficult to imagine. Scientists actually say that 2 particle collisions happen all the time. 3 particle collisions are extremely rare, and collisions of 4 or more particles are essentially never observed. So having 6 things in the same place at the same time just isn't going to happen. If you think about it just kind of from everyday experience of things colliding, if you were to come across a big wreck on the highway and you've got like 6 cars that were somehow involved in this wreck, you wouldn't think that that happened by all 6 of those cars together at the same time. Instead, what happens is sort of a chain reaction process. Like one car runs into another car and those things go sliding over here and someone else hits that, and then those get stopped and someone didn't see it in time and can't hit the brakes and they run into that. And so those things build up. Well, same sort of thing going on here. But you know what? Even if we could imagine that 6 or 5 oxygens happen to collide with a propane at the same time, then think about the other requirements to have a reaction. Not only do those collisions have to happen, but they have to happen in the right alignment of the molecules and with sufficient energy. Well, looking at how this propane is arranged, where is this oxygen going to hit to be able to attach to that and split apart with 2 oxygens on either side of a carbon, or another one, a single oxygen has to have 2 hydrogen. It doesn't work that way. So how do reactions happen then? And in fact, most reactions happen. They happen through a series of steps. Let me give you an example of that. So come over here. Here's a reaction that we use to consider the idea of collision theory to begin with. We talked about how a reaction between NO2 and CO might happen by a molecule of this colliding with a molecule of that, the oxygen transferring from the NO2 to the CO to make a CO2. It turns out, though, that under certain conditions, this reaction actually happens through 2 steps, not just 1 step. Step 1 involves a collision not between an NO2 and a CO, but between an NO2 molecule and another NO2 molecule. When that happens, an oxygen transfers from one to the other, makes an NO3, and leaves an NO molecule, one of the products of the reaction. In a second step then, that NO3 which was formed, which notice isn't one of the original reactants, isn't one of the products, that NO3 collides with a CO, and that is where the transfer of an oxygen to the CO to form a CO2 happens. That regenerates an NO2. By regenerating an NO2 then, the fact that we use two NO2s to begin with, we've gotten one of those NO2s back, and so overall we just use one NO2. We can see that the overall process that happens here is the same as that, simply by adding those two steps together. So if I take my two NO2s, NO2, NO2, and I combine them with an NO3 and a CO, and over here on the product side, I have overall made an NO3 and an NO and an NO2 and a CO2. But of course, if we use an NO3, but then form an NO3 again, we can cross those things out. There's been no using up or forming of NO3 going on. Similarly, if we use up two NO2s, but form an NO2 in the end, the overall thing has just used one NO2. And so if we look at this, we've got NO2 plus CO yields NO and CO2. NO2 plus CO yields NO and CO2. So there's the overall reaction happening through two steps rather than one step. One bit of terminology that we need here, this NO3 that was formed in step one but used up again in step two is something that we will call a reaction intermediate. So an intermediate, something that is in the middle of the reaction. It's there while the reaction is going on, but it wasn't there at the beginning. It's not there when the reaction is done. All right, so one interesting thing about multi-step processes like this, did I mention already that this multi-step process, we call this series of steps by which the reaction happens a reaction mechanism. All right, so one interesting thing about multi-step processes like this is that the rate of reaction turns out to be dependent on just one step in the multi-step process. To see how that works, let's consider a real-life sort of example. So, no doubt many of you have traveled through the Atlanta airport at some point in time. I haven't been through there in a while, but this is something that I remember from traveling through there a long time ago, how things were set up, which I thought was kind of funny, but nicely illustrates a multi-step process and how the rate of the process depends on just a single step. So at the Atlanta airport, there's a place, there are trains that you can ride from the gate to get closer to the terminal where you go and go to the baggage claim and everything. And so the place where the trains let off is a big wide hallway, and then you walk down that hallway, and when you're going to the area with the baggage claim, at a certain point you get to this escalator, and it's just a single escalator, just room for one person to stand, and you go up the escalator, and that lets you off in another big wide hallway, which takes you to the baggage claim. All right, so now let's imagine for a minute that if all of these things were operating at their maximum capacity, the airport's as busy as it could possibly be, and we're moving as many people through there, trying to get them from the gates to the baggage claim as we can. Let's just make up some numbers here, and let's say that if you were to watch a point in this hallway and count the people that went by there, if this thing were completely full of people moving, we say maybe 2,000 people per minute could go by the point that you're watching right there. Really nice wide hallway, really busy, people moving. All right, and so this escalator, one person can stand and it's moving along, and so maybe 60 people per minute, one person per second, let's say. Again, just making up numbers. Can make it up that escalator, and then again, we've got another big wide hallway here that could move, operating at maximum capacity, 2,000 people per minute. All right, so now, let's say that at this busy time, you're standing here right where this hallway lets out into baggage claim, and you're counting the number of people that come by. How many people do you think would be able to pass this point and get to their bags per minute? Like, what sort of rate of people arriving there would you see if everything works to maximum capacity and this is kind of the path that people have to follow? So think about that for a minute. Pause the video if you need to. Okay, so hopefully the answer that you came up with is right here. You're only going to see 60 people per minute crossing that point right there, because if only 60 people per minute are coming off the escalator here and there's no other way for them to get into that hallway, it doesn't matter that this hallway can handle 2,000 people per minute. Doesn't matter that 2,000 people per minute can go through here. We can only get 60 per minute up this escalator, and so that's the rate people are going to be arriving right there, right? Okay, so now let's say that somebody with the airport, someone who runs the airport, has been getting a lot of complaints that people are not able to get to their bags fast enough. They're late to their conferences, can't get to the hotel in time, etc. And so they have hired you as a consultant to come in and figure out what the problem is and try to redesign things to get people to their bags faster. So if you come in as a consultant, you say, okay, I've got a solution to the problem. Here's what we're gonna do. We're gonna make this hallway wider. Now, this hallway can handle 4,000 people per minute. And so we're gonna get people to their bags faster. No, okay, right? Doesn't work that way. If we only have 60 people per minute coming off this escalator, we're still only going to get 60 people per minute to their bags. So this step in the process here, so we can think of this as like step 1, step 2, step 3. This step in the process is what we would call the rate determining step. And the rate determining step, or the rate limiting step, you'll hear it sometimes called, is always simply the slowest step in the multi-step process. So the overall process can't go any faster than the slowest step. And so really, if you want to get people to their bags faster, what you have to do is something like make this escalator a lot wider, or add multiple escalators, or here's my favorite, speed the escalator up a lot. So maybe you can get 120 people per minute off of that escalator. However you want to do that, that's where you got to attack that problem, right? Okay, so now let's take that back to a chemical process, and we're going to see something interesting about this reaction. In this reaction, it is known that of these two steps, this first step is the slow step. The rates of individual steps have to do with the chemical natures of the things reacting there, and so this step would have a higher activation energy than this step, which makes that a slower step than that step. And so that's the slow step in the reaction. How do we know that's the slow step? Well, it turns out the reason we know that's the slow step is because of experimental measurements of the rate law for this reaction. The rate law for this reaction is that the rate is constant times the concentration of NO2 squared. Notice that this reaction has two reactants, and we have said that ordinarily we expect the rate of reaction to depend on the concentrations of the reactants. In this rate law, though, we can see that the rate of reaction doesn't depend on the concentration of CO at all, or in other words, this is a reaction that is zero order for CO. We talked about that a little bit earlier and said that that was kind of a weird thing. How is it that a reaction can have a rate that doesn't depend on the concentration of one of its reactants? If you increase the concentration of this reactant in the reaction, isn't that going to mean more collisions and therefore a faster reaction rate? Well, yes, there will be more collisions with this reactant, but notice those more collisions are going to happen in step 2, in the step in the reaction that is already faster than the slow step. And so, because this reaction can only go as fast as its slowest step, that's the rate determining step, and the only things that are going to have an effect on the rate of reaction are things that affect the rate of step 1. And step 1 doesn't involve any carbon monoxide, it only involves the NO2, and that's why that reaction is zero order for CO and second order for NO2. So another thing that's going on here is because there are two NO2s in that rate determining step, that's why it's second order for NO2. So just looking at the coefficients in the balanced equation doesn't tell you anything about the exponents in the rate law, but if you have the elementary steps, the actual collisions that are happening, and you know what the slow or rate determining step is, then you can actually predict a rate law from that, not experimentally, but in practice it actually works the other way around. Experiments are done to determine the rate law, and from the rate law then a reaction mechanism is proposed that would explain that rate law. Okay, so that is reaction mechanisms and multi-step processes and how all of that stuff allows us to see how a reaction could be zero order for a reactant. We'll also use the idea of the reaction mechanism to understand a little bit more about how catalysts work, but we will save that for another time. Good to not see everybody. It would be good to see you, but I'm not seeing you, but you're seeing me. I'll catch you again soon. Bye.